Bernhard Riemann, I did the backward reading a bit. So he lived, according to Wikipedia, he was living in these times, and he did a PhD in Göttingen for Gauss. So famous advisor, well, famous student. And Lebesgue lived, they didn't live at the same time. So that was interesting. Lebesgue actually was born after Riemann already had died. So I think these were the numbers. And where did Lebesgue do his PhD? In Paris. And guess who was the supervisor? Who else than Borel? So from Gauss to Riemann against Borel to Lebesgue. So this is kind of the story about two integrals. Riemann actually was he did an amazing job in defining the Riemann integral, and Lebesgue kind of built on that and constructed even a better integral concept. And let's see. Let's write one theorem that should kind of summarize this story. Assume that f is a function from a closed and bounded interval from a to b to the real line. And assume that we are now looking only non-negative functions, so we don't need to worry about these plus and minus signs. Okay, it will generalize too. And assume that this is Borel measurable. In the sense that the Borel sets have Borel pre-images as usual. And let's assume that it is Riemann integrable. And what does that mean? It means that this kind of ordinary looking integral notation that we have learned in first courses. So this is well defined. We'll come back to that definition in a while. If this is true, so then when we look at the Lebesgue integral of f against the Lebesgue measure on the real line, and we restrict to the set AB, then this integral matches precisely, is exactly the usual integral. And this is, of course, amazingly important theorem because we know lots of functions for which we can calculate these numbers. And all of that theory, fundamental of calculus, whatever tricks you know how to change integrals and integration by parts, all of these things extend to the Lebesgue measure and then these general functions in this new theoretic setting. Why is this theorem true? Let's do a little sketch. We need to recall what the Riemann integral means. Let's recall it briefly, the definition. You probably remember it better than I do because there are so many years when I did my basic courses in this type of math. So let's hope that I haven't forgotten everything. Think about this being a function f and that we want to integrate. How do we Riemann integrate this function? We divide this we divide this interval into small intervals, and let's call this one, for example, the interval ij. Okay. Then we look. Then we define an approximation. So we approximate this from below. So let's say by some function which is constant on these intervals. So we take a function which is constant on these intervals. So it's constant there, and let's call it g. G is constant there, it's constant on this interval, and then it goes, let's say it goes up. It goes up. And let's say that G is less than F, so we require G to be less than our target function. And that's why G is going this way. And then we have these, we get these bars to the picture. And then let's call this value here aj of the value, and then the Riemann sum of G is then the area of this what's in this bar. So the area that we approximate is then sum from J from 1 to some number k, how many intervals we have. Then we have the the area, so the area of each of these bars. So it is aj times then the length of the interval. So that's actually nice because my daughter is now in the grade 6, and for her exam in grade 6, so we had to do this bar area calculation. So now this is aj times, what's the length of the interval? Well, that is of course the Lebesgue measure of the interval. Yeah. Okay, now I'm using the Lebesgue measure, although we are speaking of Riemann integrals, but to see the connection. So the length of the interval I'm denoting by Lebesgue of this interval. That's the area. What is the function g? G is a function now that we can write. It's some function that is constant on these intervals. So we can write it as we sum over the intervals, and then let's say aj is the value on the interval. And then we can write down the indicator of that interval. So when ij denotes the interval, so then this is the ij indicator. Yeah. And the Riemann integral was defined that we studied this type of lower sums. So we defined the lower sum of f, or kind of lower Riemann sum. We define it as supremum of all g which are less than f of this type of areas. So then we write this sum 1 to k aj lambda of ij. And we do it for all g of this form. So this type of g is called a step function. Maybe different color works here. Step function. And we could denote by s. Let's say these are positive step functions with this notation. So a step function, g belongs to there if it's of this form. It's this form of step function. And of course, if you look at this g, these are Borel sets, they are intervals. So this is a Borel measurable function. G is also a simple function. So every step function is a simple function, right? Except that this notation is bad because this set is included in the set of simple functions. What's the difference? What are those simple functions which are not step functions? Well, these are the indicators of some non-intervals. For example, the indicator of the rational numbers that we just looked. This would be a simple function, but not a step function. So step functions are those functions that you can draw nicely in this way, that they are constant on the intervals, and that I here emphasize that we are looking at intervals. Okay. So we actually define the lower Riemann sum as the supremum of this type of sums of G. But and then we look at the area this way. But if you look at the area, so actually this area is nothing else than the Lebesgue integral of the function g against the Lebesgue measure. Yeah. If you like, you can plug in the box there as well, because this is a simple function, so it's a simple integral in this sense. And that's why the kind of lower Riemann sum can be written as the supremum of the Lebesgue integral of g for all g in the being simple functions and which of the step form, so simple step functions. Similarly, the Riemann integration theory does a similar upper approximation. And that's the approximation where you do the same picture, but you look at functions h which are bigger than f. And you look at ages which are, again, they are step functions. And you do a similar area for some bars which are bigger than f. So now that would be the h function would be a step function of this form, that it goes above f. Then we calculate the bars of this green function, and then, okay, green function is a nice way to mention it, but this is a green function, not green function in the sense of PDEs, but because its color is green. So these bars give a bigger area, and that's the lower Riemann integral, and this is called the upper Riemann integral. And it's the infimum again of this type of areas, but these areas turn out to be Lebesgue integrals in this sense. And with all of these drawings and definitions, so then Riemann integrability means that that this exists, and means that actually that this lower lower Riemann sum or Riemann integral this way is equal to the upper part. So there's no difference if you approximate this with bar volumes from below or above. So if these approximations give you the same number, so then you define the Riemann integral to be the common value of these two approximations. And now what the claim was? The claim was that if we have Riemann integrable thing, so then these two integrals equal to each other. Why is this true? Let's recall once more what was the definition of f d lambda. Now we look at the Lebesgue integral here. The Lebesgue integral, when f was assumed to be non-negative, was defined as the supremum of Lebesgue integrals of all simple functions which are less than f. If you compare this one there, or there actually, so these are really similar things, except that here we have a little bit smaller set of where we allow f. Here we have more functions to look in the supremum. So we optimize over a bigger space. So the supremum is bigger. So that's why we conclude that actually this Lebesgue integral is bigger. This is the Lebesgue integral, and this is the lower Riemann integral. Yeah. So the Lebesgue integral wins the lower Riemann integral in this way. What about the other direction? If h is simple step function and h is bigger than f, so then what we know about monotonicity of Lebesgue integral, so then we know that the Lebesgue integral of f is less than the Lebesgue integral of h. Remember, these are Lebesgue integrals. That's why this is true for all h of this sort. So especially then, it follows that if you take the infimum of ages of this form, so then this integral is less than the infimum, which h which dominate f and which are simple step functions. But what we have there, this was the upper Riemann integral. Our conclusion is that the Lebesgue integral is less than the upper Riemann integral, and it's bigger than the lower Riemann integral. But when we assume that the function that we studied was assumed to be Riemann integrable. So that definition means that actually this one and this one are equal. That's what Riemann integrability means. So this is why we have something in the middle of something which is equal. So it follows that yes, indeed, this must be equal to both of these quantities, and by definition they were defined to be this Riemann integral of f from a to b. End of the proof here. Let's open the statement again. Here it was. This wasn't part of the statement. This is the statement. Do you have questions about the proof? Let's do a tiny example and then we will have a break. Tiny example. What is the Lebesgue integral of, we integrate f against the Lebesgue measure in case where, let's say, a is the interval from 1 to 2. Let's say f is the function which maps x to the number, let's say, what should we choose for good x? Let's say x is, f is x third. Okay. Is this Riemann integrable, this type of function? Yes, it is. It is a continuous function on a closed interval, unbounded interval. So f is Riemann integrable. So we know that f happens to be Riemann integrable. If f is f Borel measurable, f is a continuous function. So continuous functions are Borel measurable. That's why we recall that in this case, we were looking at the setting where we have these Borel sets, and then we have the Lebesgue measure, and then now we know that this very abstract looking integral is actually equal to, in the Lebesgue setting, we would write here the integration area from 1 to 2. We would write here x third. We might write here the Lebesgue measure, and then we indicated, okay, x is the integration variable for the function. But this, by the previous theorem, it becomes the standard Riemann integral, and then we know that it is using the usual techniques. We know that this is 3.75.